researcher on modeling with a PhD from MIT, I believe. And after leaving the Planning Commission has returned to his think tank, IRADe, which specializes in issues of energy policy and climate change, while at the Planning Commission contributed a foundational report towards an integrated energy policy, and has also been assisting the Planning Commission in thinking about a trajectory for low carbon growth. And I will, Kirit, Michael Greenstone has already been on the program, so you could introduce him if you wish. And this is one of the keynote speakers that punctuate the presentation of research papers. Michael's chosen topic is Will Adaptation Save Us from Climate Change? But at this point I hand over to Kirit to take over the session.
Business in India, around the world as well. Of course, there are lots of people who feel that this is just a hoax, but by and large, I think the large part of scientific consensus is that it is a reality, the threat is real, and that we will be subjected to significant changes in climate. From India's point of view, we have really very, very difficult issues to face. First of all, it will affect our climate, and that means the hydrological cycles, patterns will change. Our agriculture would have to adjust or adapt in a very different ways, in perhaps unimaginable ways as of now. Sea level rise would disrupt, perhaps 1 meter sea level rise would submerge 7 million hectares of land, that millions of people and many of our coastal cities would be threatened. And what is even more frightening in some sense is that 1/3 of Bangladesh would be submerged, and maybe 30 million Bangladeshis would spill over into India. So you have a huge problem that we would like the world to take action to minimize the threat of it. Even though we are one of the smallest emitter in per capita terms in the world, we are emitting something like 1.8 ton of GHG per person per year, compared to 20 of the United States, 14 of the European Union countries, and a global average of 4.5. So we have really very little responsibility in any real sense for the threat of climate change. Another way to look at it is that, the climate change takes place because the greenhouse gases build up in the atmosphere. But every year of the total emissions that are made by mankind, you say that not 1 ton of the build-up in the global atmospheric climate, GHG emissions has been contributed by India. Nonetheless, since we are highly vulnerable, we have a strong interest in getting an international agreement, and therefore we have offered to take many steps ourselves. For example, in 2006, the Prime Minister at the Gleneagle Conference said that we are determined to see that our per capita emissions at no time exceed the per capita emissions of developed countries, of industrialized countries. We are far from it, but we are saying this is a huge commitment in a sense, because if we are to reduce or contain climate change to 2 degrees centigrade temperature increase, then by 2050, the industrialized countries will have to bring down their emissions by about 80 to 90%, which would mean that their per capita emissions would remain around 2.5 tons per capita. And that's what we say we will also restrict ourselves to. Secondly, we also said at Copenhagen that we would reduce our emission intensity by 20 to 25% by 2020 compared to our 2005 levels. So we are taking actions. in a way, we are not publicizing as well and as effectively as the Chinese do, but we are doing really quite a lot about it. But these are all, you could say, mitigation actions. As far as adaptation is concerned, it is something that we are perhaps doing very little about. One just hopes that people will adapt themselves, but we have a long way to go, and we need to take a lot of adaptation actions. So I was delighted to see that Professor Greenstone is going to talk about what is the scope of adaptation, and will adaptation save us from climate change? Professor Greenstone.
I think climate change is the greatest environmental challenge that humankind has ever faced. And I think it's incredibly, its impacts and its costs are going to be distributed around the globe in very unequal ways. And I think this is a good time to start to think about that. So the way I like to begin this talk is just by pointing out that there are really only three ways to deal with climate change. The first is mitigation, which was just we can reduce our emissions, we being the world. The second is there can be adaptation, where people figure out ways to confront the changes in the climate that are wrought by greenhouse gas emissions. And the third is, we're not supposed to talk about it in a polite company, but it's geoengineering, which is where we find ways to alter the impact of the accumulation of greenhouse gases. And so the reason that I've titled this talk, Will Adaptation Save Us from Climate Change, just to be provocative, I think is because to be provocative, I will say that the only one of those three techniques that we're guaranteed to use is adaptation. And let me just tell you why I think that's true, and then we'll get into the heart of this. But with respect to mitigation, I think the international efforts to achieve real reductions in greenhouse gas emissions, not greenhouse gas emissions per unit of GDP, but real emissions, which is the thing that the planet cares about, have been a pretty big failure so far. There have not been great successes to point to. And I think that is related to the fact that there aren't any property rights for the atmosphere. There's actually several reasons that this is the case. That's one. That I think a second is mitigation is quite expensive. Now I'll demonstrate that as we go along. And the third is that most benefits of mitigating climate change are in the distant future. And that's something that I think we always have a hard time with, making long-run decisions. And here, it's not just a decade or two away, but it could be several generations away. Another complicating factor for mitigation, I think, is that it's going to require at least 20 countries to agree to do something and to be serious about it. In the United States, we have trouble getting ourselves to do any one thing, so it's further complicated by, I think, having 20 countries try to do something. And then I think this is an especially salient point for today, which is, as one looks forward, the biggest cuts in emissions are going to have to come from the poorest countries, and at least relative to what their baseline emissions are projected to be. And those are the very countries who value emissions the most, in the sense that those emissions are the most valuable for human welfare. And finally, there's a technical issue of mitigation, which is that it's very hard to verify who cut what. And so I think that we don't even have a way to verify if someone promised to reduce emissions. So that makes me a little pessimistic. All those reasons make me pessimistic about mitigation. With respect to geoengineering, we don't yet have the science to do it. And then all the political problems associated with mitigation surely apply to geoengineering as well. You could just ask yourself, who's the country that gets to set the global climate? And I suspect people would have very different views on which country should be the one that gets to set that. So with all that, I think this is a great time to talk about adaptation, and I will try and do that now. And let me just say the outline is I'm going to give a little background on climate change. I think a lot of this will not be news to people here. A very brief look at what economic theory tells us about adaptation. And then I think there's really only a very nascent literature on adaptation to environmental threats. And I'll talk a little bit about that just since I know it best from my own research, but that's not to imply that there's not lots of other good research out there as well. And then I'll try to conclude. So let's just start with the background on climate change. I'll just make the point that temperatures have been rising. This is a famous graph. It shows temperatures between the year 1000 and the present. You can see that in the last 50 years, there's been a really dramatic increase in global average temperatures. This graph has become famous in the United States. Al Gore talks about that graph all the time. It's called the hockey stick graph. This is a graph, we're going to see a bunch of graphs like this, and I apologize, I'm going to have a couple in Fahrenheit and then we'll switch to Celsius. But so this is, there's lots of graphs about what happens to global average temperature. I think what they tend to miss is a really important thing, which you can only get by unpacking some of the climate projections, and that is that the increase in temperatures are not at the moderate range of temperatures. Actually, what's projected to occur are very large increases at the very hot, on the very large increases in the number of the very hottest days. And so what this graph is trying to say is if you look at the white bars, those are the average number of days that the typical American faces in different temperature ranges. And so you can see the typical American faces about 70 days a year with the temperatures between 60 and 70. This is Fahrenheit. And then I think most important for this graph, if you go look at there's about 1 day a year that the average American faces where the temperature exceeds 90. And I'll show you a graph like this for India as we go along. And just to put that into perspective, just to make sure we're talking about the same thing, the 90 degrees is the average of the high and the low. So that's a very, very hot day. So that's, I think 90 is about 32 C. So a 90-day, the average of the high and the low would have to be greater than 32. And what's striking about this graph is not the current distribution, but what's projected to happen if we don't do kind of on a business as usual scenario about the climate. And what's projected to happen is that there will be a really dramatic increase in the number of days, the very hottest number of days. And so in this case, from this climate prediction, from the Hadley 3A1FI scenario, there'll be about 30 extra days that the average American would face with the temperatures greater than 90, and maybe about 20 extra days with temperatures between 80 and 90. And the reason that it's so important that all the extra hot temperatures are concentrated there is that's where all the bad things occur. They don't occur if you had a few extra days that were in the 60 to 70 range. They occur at the tail of the temperature distribution. And those bad things are crop failure, mortality increases, and I'll try and demonstrate some of them as we go along. Okay, so there's a long list, some of which were just mentioned, of things that we think are likely to go wrong or not improve with climate change. Here's just, I went to the fourth report of the IGC to pull together some of them, but increased water stress, increased mortality and morbidity, reduced farming productivity, a series of things, none of which are very good. Okay, so that's climate change. So the next point I want to make here is that stopping climate change is going to be extraordinarily expensive and will have to be done from around the world. So you can see this is, so first of all, let's stipulate the U.S. does not currently have a climate policy, so that's not to imply that there is a climate policy in the U.S. But what that graph is meant to show is atmospheric concentrations of carbon dioxide at by the end of the century with and without a U.S. climate policy. And so they would be here if if the U.S. kind of goes on its business as usual scenario, and they would be just a little bit lower if the U.S. were to adopt something like what was just outlined, 80% decline by 2050 and further declines after that. And so the point is, it truly is global climate change And all the countries of the world are going to have to participate in reducing emissions if greenhouse gas carbon dioxide concentrations are going to be held at either 450 or 550 or I think beyond that the scientists get very scared. But the scientists would like it to be at 450. And right now we're projected to be 700, and I think this is probably an underestimate, to be honest.
And 2 degrees will be?
About 450. And for some reasons that I think are too technical to go into, I think this is probably really an underestimate of what global concentrations would be without any climate policy. Okay, but here's an example of what would be asked of developing countries. So here's China. And this is China's business as usual emissions. So they're about here now. They're about 6 or 7 billion tons of CO2 equivalent per year. And they're just projected, that's projected to grow you know, at a very fast rate. Probably more than, to the end of the century, to more than 20 billion tons per year. If the world were on a path to 550, remember we're not on a path to 550 right now, but if the world were on a path to 550, there's different ways to divvy that up, but kind of a standard way to do that would require China to do this. And you can see it's this space between these two lines that would have to be filled in. Now, so let's think about that. That's a very large reduction in greenhouse gas emissions. And here's why I think I'm not terribly optimistic about mitigation. So what does that mean to have a large reduction in emissions? That basically means that, you know, there's a lot of talk about green growth this and green growth that, but what it really means at its core is buying more expensive electricity. That's, if you cut through all of it, that's really what it means at the end of the day. And here are some estimates, I think they're up to date from the United States, of what it would cost to produce 1 kilowatt hour of electricity from various sources. And you can see why people love coal, even though it has terrible health effects. It costs about 3.2 cents a kilowatt hour to produce, 3.2 cents to produce 1 kilowatt hour of electricity. At current natural gas prices, it's about 5.5 cents to produce one for natural gas in the United States. New coal, which in the United States now has to have all kinds of extra clean air, abatement equipment attached to it, would be about 6 cents a kilowatt hour. And now let's go to what would be zero carbon electricity sources. And here's new wind. And what I want to just highlight is the problem with renewable technologies is that they're intermittent. So the wind isn't always blowing and the sun isn't always shining. But to run a real electricity grid, you have to have electricity going all the time. And so what I've created here is what I like to call kind of a Frankenstein plant, which is it's a wind plant that has a natural gas backup sitting next to it. And so when the wind's not blowing, the natural gas plant will turn on. And that's a standard, would be, given the current battery technologies, would be a totally standard thing to do. And in an optimal place in the United States, that would be 9 cents a kilowatt hour. So let's just remind everyone that we were at 3 cents a kilowatt hour for coal. Instead, you could triple the price of electricity to have the wind plant in a really good place. In a not so windy place, it would be even more expensive. Nuclear is probably 11 cents a kilowatt hour. And we're not going to be building a lot of those in the United States, I don't think. And solar, again, a Frankenstein solar plant is about 12 cents a kilowatt hour. So the point that I'm trying to make is, if we want to fill in this gap for China or the United States to fill in their emissions reduction, at the end of the day, what you're really doing is you're asking people to buy electricity that's 3 or 4 times more expensive.
But those are current costs, not costs taking into account any future technological innovations.
These are current costs, and tomorrow might be a better day. That's always true.
I mean, in this point, what about nuclear fusion? Have you taken care of that in account?
I think we're at the edges of what I know, but I don't think that there's anyone who thinks, among my energy colleagues at MIT, I don't think there's anyone who thinks nuclear fusion is about to be cost competitive. But that, and remember, I'll I don't mean this unkind, but there's a joke about solar. And the joke about solar is that it's going to be cost competitive in 5 years, and that that's always true.
And only in California.
And only in California. Okay, so this is all a long way of saying, gosh, it might be pretty expensive. And then plus, you want to talk about the future, the world is about to become awash in more fossil fuels. Thanks to new techniques to obtain both natural gas and petroleum, there's suddenly way more natural gas, or way more fossil fuels, be it through natural gas and petroleum, at really inexpensive prices than we thought probably even 2 years ago. It's the greatest change in the energy system in the last 50 years. And then you can add on that there's just tons and tons of coal in the United States, there's tons of coal in China, there's tons of coal in India. Okay, so Thomas Edison was an inventor in the United States around the turn of the 1900s. So the famous quote from him, I put my money on the sun and energy. What a source of power. I hope we don't have to wait until oil and coal run out before we tackle that. I'll just leave it at that. So now, on the other hand, I don't want to minimize that the costs of climate change are surely going to be big. So here's just from some models, which are kind of these, on the y-axis, you've got the loss of GDP associated with different changes in degrees Celsius of temperature, and these are from different models. And you can see it really starts to turn up. I think, there's a very good chance we'll be in this range of 3 to 4 degrees by the end of the century. Okay, so I'm just going to do a brief little bit on, there's some lines of algebra that I took out last night when I was at 1 in the morning trying to tighten this up. Hopefully you guys will excuse that. I think the point I want to make about adaptation is just that just because mankind has found ways to adapt to things does not mean that it's been free to do that. And that when one comes up with the full cost of adaptation, it's not enough to simply say that we have conquered polio. We had to spend a lot of money to conquer polio, and that in adding up the full cost from an adaptation approach requires all the money will have to go into developing those changes. So now I'm going to talk a little bit about a series of papers, one of which is published, one of which is working paper, and one of which is an idea plus, but not much more. That all relate to adaptation to high temperatures and the impacts of high temperatures on well-being. So this is with my colleague Olivier Deschênes, who's at UC Santa Barbara, and what we try to figure out is what are the impacts of extreme temperatures on mortality in the United States, what are the impacts of extreme temperatures on adaptation, and then try to come up with some estimates on what would be the cost of climate from a highly constrained adaptation approach. So I'm going to show a bunch of graphs like this. Let me just go through this one slowly. This tells you the impact so these are the number of days in the year. This is from a regression that relates the mortality rate against the number of days in the year that the temperature fell into each of those 10-degree wide bins. And the way to interpret it is, if you moved a day from 50 to 60 degrees, say all the way up to greater than 90, that would increase the mortality rate by, in this case, you can read that that's 0.8, by less than 1 death per 100,000 people. And similarly, if you took a day from 50 to 60 and put it at less than 10 degrees, that would increase the mortality rate by about 6/10 of a death per 100,000 people. And so this has a kind of the famous U shape between temperature and mortality, but truthfully it's a pretty flat U, and you'll be able to see exactly how flat that is in a couple minutes. Okay, so this is the first result is that the relationship between temperature and mortality in the United States is pretty muted. And the question is why? And I think an obvious answer comes from this, which is I'm going to call electricity consumption a form of adaptation. And what's truly astonishing about this is we have this flat relationship with mortality. Well, why is that? It looks like it's at least partially due to this incredible increase in energy consumption that occurs on really hot days. And now, obviously, that increase in electricity consumption is by more than mortality reductions, but it is definitely part of it. And I think it highlights that at least in the United States, there's pretty good opportunities for adaptation as it relates to mortality and temperature.
Why wasn't that the same view in increasing heating costs to correspond to the increasing cooling costs?
Yeah, part of it is that I think people use natural gas for heating in the United States in the Northeast where the temperatures are really coldest. I don't have a great answer, but I think so.
No, the clear answer there is if you want to, if it's hot room, if you want to cool yourself, you have to cool the whole room. And if it's cold, you can bundle up. You can put on a sweater and a coat. You don't have to heat the whole room. Whereas with a hot room, well, you got to cool the whole room. So it's asymmetrical.
So here, just as a reminder, this is the change in the number of days in each of these temperature bins. This is now, I'm showing it from two different models, two different climate models. But if you take those, what they add up to is that if you just zoom the United States to the end of the century, you'd have about a 3% increase in the annual mortality rate. And to put that in perspective, that's actually, I think, quite small. In the last 35 years, the U.S. annual mortality rate has declined by about 1% per year. So that's like saying over the next 90 years, if we suddenly had climate change happen overnight, there would be, we'd lose about 3 years of technical advance on mortality rates. In contrast, there's a larger response in electricity consumption, which appears to be highly related to cooling. And I think it underscores individuals' willingness and ability to engage in costly adaptation in response to high temperatures. Okay, so now maybe a slightly more salient part of this talk, given that we're in India today, is this is a paper with Robin Burgess from the IGC, among other places, also with Olivier Deschênes, my colleague Dave Donaldson, and Weather and Death in India, Mechanisms and Implications of Climate Change. Okay, so I think the results in the United States were somewhat flat impact on mortality and a big impact on electricity consumption. I don't need to put this up here. Let's just get down to the heart of it with India. So here's the distribution of days in India. So this is what the average person in India faces. I guess the modal day is between 26 and 28 Celsius. The average person faces about 3 days a year where the temperature exceeds 36, and you can see the full distribution. And so the key key difference here is, of course, India is hotter than the United States, and India is less wealthy. So if you go to these same two climate models that I showed you a couple minutes ago, the Hadley 3 model with the A1 FI scenario, for those of you who are into climate models, and then the CCSM 3 model with the A2 scenario, they would imply these changes in the number of days in each of these temperature bins. And so you can see it's just like in the United States, there's an incredible increase in the number of days, greater than 30 or 32, that are projected for India by the end of the century. Okay. So what exactly happens in India when you have really hot days? All right, so the first thing is agricultural productivity goes way down. And the way to read this is that one extra day with the temperature greater than 30, if you move that day from the 22 to 24 range, reduces annual agricultural productivity by about 0.5 percentage point. So if you want to just add that up for yourself, you can see there's going to be, 50, 60, 70, 80 extra days like that a year. And so this is really an enormous decline in agricultural productivity. Second way to measure that is by looking at the wages of wage earners in rural areas. And this has kind of the same feature, that once the temperature gets above 32, their annual wage rate declines by about half a percentage point for each additional day greater than 30 or maybe greater than 32. Okay. All right, so next is I want to look at mortality rates, just like we looked at with the United States. And so let's set this up on, these are from regressions for India's case. You have, so 1 extra day with a temperature above 32 increases the annual mortality rate by about half a percentage point. So it's a dramatic increase. And I think what this underscores is that there are wildly different adaptation opportunities in India and the United States. And I think this also underscores why I'm so pessimistic about climate change mitigation is, what would be the best thing that could happen to India? Well, it would be to have the blue line. The red line is a terrible way to live. There's terrible rates of mortality. There's terrible reductions in wages. There's terrible reductions in agricultural productivity. And the best way to do that is to use, unfortunately, inexpensive fossil fuels for electricity. And I think, the one way to say it is that the bad state of the world for climate change, which is when the climate changes a lot, is probably the good state of the world for India and China. And the reason it's a good state of the world for them is because they've got to, grow by using very inexpensive sources of electricity, just as the developed countries use. Okay. One other thing I can do with this data is separate out rural areas and urban areas. It turns out that almost all of the impact is coming from rural areas. So an extra day at greater than 36 is worth about a 1.3% percentage point increase in the annual mortality rate. So if you had 10 of those, the annual mortality rate would increase by about 13%. And it has this very, very disturbing feature of strong relationship between high temperatures and mortality rates. Okay, so just to try and summarize, in India, hot days are associated with very sharp declines in agricultural output, very sharp declines in rural wages, and very sharp increases in mortality rates. If you were to add up all those extra days that are projected to occur by the end of the century, and India remained exactly as it is today, then there would be an enormous increase in the annual mortality rate by the end of the century. I think it highlights that at current income levels, India probably has fewer adaptation opportunities, and underscores that there's going to be tremendous pressure to grow per capita incomes to get the flat temperature mortality response function that wealthy countries have now. Okay, so here's
the urban mortality rate. The graph is there.
I don't have it there, but it's the urban rate is pretty flat. There's an upturn at the high temperatures, but it's nothing like in the rural areas. Okay, so now here is a completely preliminary set of results from a historical study in the United States, which is with a series of co-authors as well. This is the same exercise that I've been doing, but now this is just in the United States, and it's looking at 3 separate periods. The blue line is from 1910 to 1939. The green line is from 1940 to 1969. And the red line is more or less the present, 1970 to 2004. And what's striking is that somewhere between that blue and the green line is basically India today in terms of the responsiveness of mortality to high temperatures. But over time, this great responsiveness has declined dramatically. First from more than a 1.5% increase in the annual mortality rate for each extra day, down to 0.8, and down to basically 0. And what this paper, which is just an idea at this point, it tries to do is to try to understand, well, what were the things that modified the temperature-mortality relationship? And we have a series of hypotheses that we're collecting data on. One is chlorinated water supply, the other is electrification and air conditioning, and then the third is hospital access. And purpose of this is to identify what are the most effective ways to modify that relationship, and what are the most effective ways to adapt to high temperatures. So that's ongoing.
So the point too is like once again putting up demands on the electricity system.
The thoughts are that climate change is projected to lead to really, really big changes in our environment. I think mitigation is going to be extremely challenging politically and economically. Adaptation is the only, in my view, form of dealing with climate change that we're guaranteed to use. Adaptation is costly. Opportunities for it are likely to be unequal across the globe, at least at current income levels. And the empirical evidence on the history of adaptation and environmental change is nascent and largely focused on short-run adaptation to the, I think, the IGC and ISI and other places should be focusing attention on trying to identify successful adaptation strategies to climate change. Okay, happy to take questions.